Swayam Prabha. Digital India. Educated India.
Welcome to module 7. In this module, we are going to discuss on heat exchanger, and a heat exchanger is a device in which exchange of heat between a hot fluid and a cold fluid takes place. Okay. Now, in the first lecture, this is that is the today's lecture, which is the first lecture on this module. We are going to discuss first on the various type of heat exchangers. Actually, in the module of heat exchanger, we are going to discuss various types of heat exchangers. Then we are going to discuss various design methodologies for heat exchangers, and then we will take up some problems to demonstrate how to apply those the various methodologies. So, in series of lectures subsequently we will be discussing all those. To start with, in the very first lecture, we are going to discuss on the various types of heat exchangers. And as you know that heat exchangers can be classified as there are 4 types depending upon the various cases. First thing is that type of contact. So, then there is a type of construction, type of flow arrangement, and type of surface compactness. So, we can classify heat exchanger based on the different views, based on the different type of situations. Like type of contact means that how the hot fluid and cold fluid, whether they are in contact or not. So, it depends upon that this is divided into 2 parts, that is called direct contact and indirect contact. Here in case of direct contact, that hot fluid will be in touch with, will be in direct touch with the hot fluid, will be in direct touch with the cold one. In direct contact, there will be a barrier. Similarly, the type of construction, how the heat exchanger is being made, we will see all the descriptions we will be seeing in details, like tubular, then plate type, then extended type, extended surface heat exchanger, and regenerative. Already tubular heat exchanger, there can be, these are the most important one, the double pipe and cell and tube, and there are some spiral tube heat exchangers, and then plate types, and then extended surfaces in the, and we have already discussed to some extent on this, that extended surface heat transfer, that the application of fins on the surface of the heat exchanger, and then regenerative, where that heat is being taken up by some material and then being used up again by the other fluid. So, it is a kind of regeneration, that means heat is being used, it is being used to increase the energy of some material from a fluid, and then that energy again will be used up by the another fluid from the material. So, this is regenerative, and then we have that, then again the type of flow arrangement can be single pass, multi pass, we will discuss all this, and there can be parallel flow, counter flow, and so on, cross flow, all these things will be there. So, they are common to each other again. And then type of surface compactness, some of them are called as a compact heat exchanger, some of them are non-compact heat exchanger. For example, that we know that extended surface heat exchangers are usually a compact heat exchanger, whereas plate and frame filter heat exchanger is also a compact heat exchanger, whereas cell and tube heat exchanger or simple double pipe heat exchangers are not called as a compact heat exchangers. Anyway, so these are the various types of heat exchangers classified in the, depending upon their issues, like how they are contact, how they are in contact, how what is the construction pattern and how they are constructed, and then what is the flow arrangement of the fluids. So, what is the surface area for this heat exchange. So, depending upon the various parameters, okay, the heat exchangers can be classified. Now, what we will do is, to start with, we will first see that type, based on type of contact, there are 2 things, one is the direct contact and another is indirect contact. So, to start we will see that direct contact heat exchanger. Now, direct contact heat exchanger means that, as I told already, that the hot fluid and the cold fluid will be in direct contact. There will be no separation or there will be no barrier between the two fluid streams. Okay. Now, it is many a times it is used, like for example, like a very common use for us is that in cooling tower, the utility water is cooled by contacting with upflowing air. So, what is being done in this case? Utility water is cooled by contacting with upflowing air. So, that is one, that air and water is in direct contact and they are exchanging the energy. So, this is the heat transfer that has been taking place. So, this becoming a case of direct contact. Similarly, in case of some evaporations, the vapor from an evaporator are condensed, vapor from an evaporator is sometimes condensed by cold water. So, this is becoming in the direct contact, because from the evaporator it is nothing but water vapor that comes, and it is, if you put directly the evaporator vapor into the cold water case, then it will be immediately condensed. Similarly, the cases of some hot oils sometimes are directly cooled. Hot oils are sometimes directly cooled, okay, with cold water, fine. And there are, so in addition to this, so there are some other cases like say distilled fatty acids, typical example of distilled fatty acids. Are cooled with water. So, in direct contact, and then sometimes then another thing like heat exchange in case of say packed bed, so or fluidized bed. So, heat exchange in packed bed or fluidized bed, the heat exchange between solid and fluid. So, this is not only in packed bed or fluid bed, not only in case of in any kind of solid fluid operations where the fluid is in direct contact with the solid. Okay, typical example is also adsorption or any other reactor, packed bed, distillation, all these fluidized bed reactor. Everywhere there is some kind of heat generation. So, some kind of temperature difference will be there in the solid phase and the fluid phase, and then there would be some amount of heat transfer that will take place, and this heat transfer is also again an example of direct contact heat transfer. Now, the point is over here I would like to say that then there are certain advantages of the direct contact heat transfer. The advantages of the direct contact heat transfer is that it avoids the extra resistance of the boundary or the barrier. So, avoids the extra resistance of the barrier between the fluids. So, we have a hot fluid and a cold fluid, and if we put a barrier, that which is the case for indirect contact heat transfer, under that situation if the extra barrier will give some additional resistance for the heat to be transferred. So, by using the direct contact situation, we can reduce that extra resistance, but that advantage, though this is the advantage, but there are severe disadvantages when you will go for a direct contact. So, disadvantages are that mixing between two fluids. Okay. So, when we will go for the direct contact, then the fluids will be mixed, and if the fluid these two fluids are mixed up, and if they are not separable, then that is the major problem for us. So, even as we have given the examples of oil in water, cooling of oil by water, or air cooler, in all the places what we have seen is that the two phases are separable. So, one phase can be separable with the other, and therefore, that type of situations direct contact can be useful, but in other situations direct contact cannot be made to be used. Okay. So, we have to see that when fluids are easily separable, okay, then only direct contact is useful. Otherwise, it becomes difficult to use direct contact heat transfer for transfer of heat from one fluid to the other one. Okay. So, now that we will see that most of our chemical engineering applications, we will see that indirect contact heat exchangers are mostly used. That means, there will be a barrier between the hot fluid and the cold fluid, and to start with, we know the very common one is that, very important one is that a double pipe heat exchanger, and here a typical sketch is given for a double pipe heat exchanger, and we can see that in this double pipe heat exchanger, what happens in case of double pipe heat exchanger, there will be two concentric pipes are there. You can see that this is the inner pipe, this happens to be the inner pipe, and this is the bigger one is the outer pipe, and this inner pipe and the outer pipe, inner pipe, they are usually coaxial in nature. Okay. And then what happens, you can see from here that that this inner pipe and then between the outer pipes, these outer pipes are connected by certain flange arrangements, and the inner pipe, there is a bend of the inner pipe that is being seen here, and this is called, when we have this kind of arrangements like that, there is a bend and then again it is coming to the other side. So, this way, that is a U-tube kind of things or helical arrangement of the inner pipe. This is sometimes called as hairpin arrangements. So, we will say that some important points for double pipe heat exchanger. Important points are that the fluid flows through. So, I should say fluids flow through tubes / pipes, and they are coaxial, and then what happens is coaxial, and also you can say that, and concentric. Okay. Now, what can happen, that outer tube, outer one acts like a jacket, okay, of the inner one. Now, the very important kind of consideration is that the hairpin construction. Is most important. So, this hairpin construction means, as I told you, that that means it's like a hairpin, and then it takes another bend and the lobe, it goes on like this. So, one hairpin is connected with the other hairpin, and that grows like this way, one by one it is connected. And this way what we can do is that we can have a stack of such hairpins, making or giving us a lot of room for the heat transfer, that means lot of surface area can be generated like this way. Otherwise, if we don't bend the tubes or pipes, then what will happen? We have to take a very straight length, long length of the tubes would be necessary, which is totally impractical. So, to make it a practical one, the tube long length of the tube has to be coiled, and this coiling is in the form of hairpin. Okay. So, some U bend will be there, and it happens like that. So, now what happens also we can see from here that some part of this bend of the tube, whatever is seen, this the bend of the tube, this can be this bend of the tube, inner tube may be surrounded by the outer jacket, or outer pipe may not be. So, if this is not surrounded by the outer jacket, then we can say that this part is not involved in any kind of heat transfer between the two fluids, but the other part is involved. And important thing over here is that because of this bending of the tubes, we may have to put some extra thickness for these U tubes, because otherwise what will happen for these tubes, because otherwise what will happen, that while bending it may be thinned in such a way that it may not last for a longer time, it may not be withstandable with respect to high pressure. So, we have to the design of this tube thickness has to be accordingly, we have to take care of this bending action on the tubes. Now, what I was telling, that hairpin construction is the most important for double pipe heat exchanger. In addition to that, we should say that double pipe heat exchanger is usually being used for a low heat duty, in case for low heat duty situation. That means, when we have less amount of heat to be transferred, less amount of fluid is to be handled, all these situations double pipe heat exchangers are normally used. And the low heat duty means the range, we can say the less than 500 kilowatt in this range. And then a packing and gland arrangement is near the inlet and exit ends of the hairpin assembly. Okay. A packing and gland arrangement, okay, near the inlet and exit ends, okay, of the hairpin assembly provides sealing to the annulus and supports the inner pipe. It means, suppose we have these. So, this portion, otherwise here in this region there should be a packing arrangement and gland arrangement, otherwise what will happen? The material will go out. So, this and this also support the tube also. So, this is what is being meant by that particular point, and we can see that the flow arrangements in this case. So, it can go like this, this is the tube side flow and this is the cell side flow. When the cell side flow is like this, then it becomes counter current. So, it is in the opposite direction, and if it would have flown like this, or if the tube side flow is like this, then it is in the co-current position. The flow will be in the co-current manner. Okay. Now, also we can say that opposite ends are joined by U bends. Okay. That means, this is what is being said. You can see there that this portion is the U bend and that is a separately joined here. So, this is the tube, this is another tube and the U bend is joined with a flange arrangement, U bends are joined with a flange arrangements. Okay. That is easy construction actually for the tubes. Then we can say opposite ends are joined by U bends and the joint is through union and welded joints. Okay. Then there are more things like that, as I told you, that U bend may or may not be outside outside the jacket. Okay. That means that if we see that in this figure, we have shown that here the U bend is outside the jacket, that jacket does not cover up that part, and so while we will be doing the heat transfer calculations, we should see that that part is not being included while doing the calculations. Okay. Then as I told you, the flow through double pipe heat exchanger, okay, can be parallel flow, also it is called, or parallel flow or anti-parallel flow. So, this is again that also they are called counter or co-current flow, counter current flow. So, this if we know that if we have a tube length of this kind, this is a length already we have seen, and this another situation, this is the station 1 and this is station 2, this is station 1 and station 2, and these are the temperatures in this region. If we say this is temperature, and we know in case of parallel flow, or if I say this, so this is the case for, this is the temperature profile for hot fluid, and this is for cold fluid which is heated up in the same direction they are flowing, and we know that this is the case of parallel flow. So, this is hot fluid again, and the cold fluid, this is the case of anti-parallel flow, not parallel flow, it is the cold fluid. So, this parallel flow, this is the case for, also it is called a case for parallel flow, also called as co-current flow, and this case it is called anti-parallel flow, counter current flow, also it is called counter flow. So, different nomenclatures are being given for this kind of situations. So, we can say that in double pipe heat exchangers, it will be mostly or rather it will be almost a perfect parallel flow or almost perfect anti-parallel flow or counter current flow. And also if we can just see that in this region, when there is a bend region, if there is a heat exchanger in this region, then here the flow is not perfectly parallel or perfectly anti-parallel or counter. If the jacket continues to cover the bend also, and if the heat transfer takes place in those region also, then it will never lie, it will never remain, this portion will never remain as purely parallel or purely anti-parallel. So, this portion will be a mixture kind of thing. There can be some kind of cross flow kind of situations will be there, because the directions is not exactly being, because there is a change in the radius of curvature. So, it will not be perfectly parallel or perfectly anti-parallel flow. In other cases, when there is a straight pipes are there, when there is a straight pipes, then they are the cases of perfectly parallel flow and perfectly anti-parallel flow. So, when there is the case when it is not perfectly parallel or anti-parallel, then we will see in case of cell anti-heat exchangers later on that there will be some corrections to be used. Correction in the sense, because we have to find out in case of heat exchanger one important parameter, that is called driving force. Driving force is the temperature difference, and this temperature difference is usually being found out with the help of log mean temperature difference. I think I have discussed in some lectures much earlier that log mean temperature difference can be calculated. The expressions for log mean temperature difference can be estimated, can be found out by doing some theoretical analysis, and we have found out for parallel flow and for counter flow how the expression for log mean temperature differences are. Okay. But this log mean temperature difference, though it is used as a driving force for heat transfer, but that may not be perfectly useful for all situations, and we may have to use it with little caution by using some correction factor. We will be discussing this in some subsequent lectures. Okay. Now, next part what we are going to do is discuss is that indirect contact heat exchanger, and the most common one is that cell and tube heat exchangers. So, this diagram shows us that a typical diagram of a cell and tube heat exchangers, and a cell and tube heat exchangers which is most commonly used in chemical process industries, and we feel that a chemical engineer should be very much comfortable with the kind of design, with all the parts, all the issues related to cell and tube heat exchangers. So, it should be discussed in detail, and we will try to discuss the cell and tube heat exchangers in a little detailed. So, if we see look onto this picture, we will see that it consists of several parts. So, we will go by one part and try to see that what is what. First part is that cell. So, in cell of tube heat exchanger, what is happening is that a tube bundle, if you first see that a tube bundle, so these are all tubes, okay. The tubes are being placed in some cells, okay. And we will see that to start with there are several things. First one is the cell. So, cell means it is a bigger pipe. Cell is the enclosure and through which the cell side fluid passes. Okay. So, cell is an enclosure of tube bundle and allows the passage of cell side fluid. So, therefore, in case of cell and tube heat exchange, both the fluids will call one will call as a tube side fluid, another one will call as a cell side fluid. In case of double pipe heat exchanger, one could be called as the annulus fluid, another will be called as the inert tube fluid, but here the cell side fluid and the tube side fluid. So, in the cell, cell is usually a bigger in size. When the cells are very big, for big size cell, it is being done. How it is being fabricated? That it's a metal plate is rolled over to give a cell, and then welded in the axial direction. So, a metal plate is rolled. The plate is under heat treatment. It is in thermal treatment. So, it is hot, and then it is rolled, and after it is rolled to a diameter of a specific size whatever we require, and then in the longitudinal direction or in the axial direction this is get welded. Okay. And so, that the metal sheet, that metal plate which is being taken to make the cell should have that calculation is simple calculations. The width of or the breadth of the metal plate should be equal to the length of this cell and tube heat exchanger, and the length of the metal plate will be equivalent to pi into d, 2 pi r basically. Okay. And when the selection of if the diameter is less than 60 centimeter, then a pipe of suitable thickness can be used. Can be used as cell. So this is what from the construction point of view. So cell is a bigger diameter pipe. That pipe is made either by rolling of a metal plate and then doing an welding, or by just cutting a bigger suitable size pipe piece. Okay, that can be used as a shell, and the cell purpose of the cell is that it will be the tube bundle will be placed inside, and it will help to passage for the passage of the cell side fluid. And then the material of construction also very important for this cell side fluid. Material of construction, MOC, it is usually carbon steel is a very common one. Okay, it's a very common material of construction. Now, this materials of construction is definitely dependent on the operating conditions and also the fluids to be used. So, operating conditions, means temperature, pressure. These are main operating conditions. Particularly the temperature is very important, because the fluid reactivity or the corrosion behavior of one fluid on a metal surface depends on particularly the temperature. Okay, and then the fluid, type of fluid to be used. So the most important part has to be is to see that the fluid which is used for heat exchange, which is passing through the cell side, should not corrode the cell side surface. Okay, that is what is of importance. Now, this is the cell. So, and then next part is the tubes. That is very important. So we can see that. So we can see that the tubes are naturally of very lower in size, and they are placed inside the cell. Now, how the tubes are placed? These tubes are basically they provide the surface area of the heat transfer, because as we understand, the tubes are walls of tube walls. Okay, tube walls separate the two fluids and act as surface for heat transfer between the two fluids. Okay. Okay, and fluid flowing through the tube is called tube side fluid. Called as tube side fluid. Okay, and then usually the material constructions used in this case carbon steel, then stainless steel, then cupro nickel, copper, brass, aluminum, etc. And again, that choice is depending on MOC, choice of material of construction depends on the application. That means, again we should say that operating conditions and the type of fluid to be used. Okay. Now, many a times fin tubes are also used. We have discussed previously, fin tubes are also used to increase the surface area, and this finning is can be longitudinal fin tubes, it can be radial fin tubes. Usually the longitudinal fin tubes are very common in this kind of situations, but most of the chemical engineering applications, they do normally use simple tubes, not even the fin tube. Fin tube heat exchangers are usually called a compact heat exchangers, and we know when to use the compact heat exchangers, already we have discussed, but it is again to say that when the heat transfer coefficient between the fluid and the wall surface is very less, under that situation what you have to do is we have to increase the surface area, because if you know, if you see that Q is equal to U A delta T, and this is U is the heat transfer coefficient, okay, and delta is the temperature difference, and this A is becoming the area of heat transfer, sorry, area of heat transfer. So, if I have three possibilities in my hand to see the heat transfer rate, okay, that Q dot, if we say heat transfer rate, to see the heat transfer rate, I have three possibilities. One is U, that heat transfer coefficient, I can increase. So, but I have some limitations. We know that with increase in Reynolds number, heat transfer coefficient can be increased, but after we reach the turbulence region, then further increase in heat transfer coefficient is not possible. Then delta T, driving force, that the temperature difference, it is normally it is decided by the external world, how much temperature changes I can do, that is already being defined. It cannot be done by infinite difference in temperature, cannot be made, it is not possible, it is already defined by the external world. So, the remaining possibilities is that area of heat exchanger, while we have discussed that fin heat exchanger, that fin type heat exchanger that we have discussed, extended surface heat transfer, that time we have discussed that area is the only possibility by which we can largely change the heat transfer behavior of heat exchanger and of a heat transfer surface. So, therefore, that in case of when there is a heat transfer coefficient is less for some fluids, solid system, particularly air to some solid surface, the heat transfer coefficient is very poor. Under that situation, we may have to use increased area, and that increased area is only possible by putting the fins, and that ultimately in turn looks like a compact heat exchanger, where as you have seen that it is some definition is given that 700 meter square per at the very beginning. Here 700 meter square per meter cube, if the surface area density is like that, if surface area density is less than 700 square meter square per meter cube, then we call it to be compact, otherwise we call it to be non-compact, otherwise we call it to be compact heat exchanger. So, this is just a typical information about that. Now, let us come back to our tube side regarding the details of the tubes. Now, tube sizes, there are some standard sizes of the tubes are available for the heat exchangers. So, this is usually 3 by 4 inch, 1 inch, 1 by 4 inch, then 1 by 2 inch. So, these are the typical sizes of the tubes. Now, narrow tubes, if I want to use narrower tubes are used for smaller heat exchangers with and when working with clean fluids, because the important point is if the fluid is dirty, and we are using narrower tubes, then what is the possibility is that narrower tube, the clogging of by the tube holes will be clogged by the darts, and therefore, the flow rate will be drastically reduced and there will be huge amount of pressure drop that will be occurring. Okay. So, that will really create a large problem, big problem in the flow situation in the heat exchanger. Okay. And then tube thickness, it is usually governed by Birmingham wire gauge BWG. This tube thickness is dependent on various factors. These are operating pressure, then we have corrosiveness of the fluids, to be handled, and then thinning of tube wall during bending, So, this is particularly the case when you have U bend cell and tube heat exchanger, U bend type. Heat exchanger. Okay. Now, length of the tubes are pretty standard. Um, 8 feet, 12 feet, 16 feet, 20 feet, 24 feet. These are standard lengths. Other lengths are also used. Okay. And then now the arrangement of the tube arrangements, that is very important. So, how the tube is arranged? So, this is called based on the pitch, that is, it is called square pitch. Already we have discussed. And this is called triangular pitch. Square pitch arrangement and triangular pitch arrangement. In case of square pitch arrangement, that it's like this. So, this is a square, and the center to center distances, if they are joint, this leads to a square. Okay. And the triangular pitch usually is a, if the center to center distances are joint, then it gives an equilateral triangle. And usually these angles are 60 degree, and 60 degree triangular pitch is a very common. This is sometimes also called as 60 degree triangular pitch, and it is very common. And we can see that this distance, the center to center distance, this is called the pitch, PT, square pitch, and this portion is nothing but the clearance, C is clearance. Okay. Similarly, here this is the center to center distance, this one is called PG, that the triangular pitch of the triangle. So, center to center distance between two tubes is called the pitch, whether it is a square pitch or the triangular pitch. In both the cases, these are called pitch, and in square pitch these angles are 90 degree. Okay, and it makes it square, and in this case it makes it's a triangle, and the triangle is usually an equilateral triangle is being formed. That means they are at 60-degree angles. Okay, and that we know that there are certain situations that if we say the square pitch versus triangular pitch, what happens, this is in this case particularly for triangular pitch is favored, because here we can say more heat transfer area per for a fixed cell in comparison to square pitch. Okay. And then we can also say that in this case the pressure drop is more due to more turbulence, and as a result what will happen is that therefore more heat transfer coefficient is achieved. But in case of square pitch, what is happening, it's an easy cleaning operation. As compared to triangular pitch. And we can say that less pressure drop, okay, and less pressure drop and heat transfer coefficient as compared to triangular pitch arrangement. Okay. Now, what happens is that the next important point is that the tubes, how they are fixed in the cell. If you see that the tubes are placed, inserted into these are called tube seats. So, these are called tube seats. So, tubes are placed in the tube seat. Okay. So, these tubes are placed in the tube seat. So, you have certain holes in the tube seat, and through which the tubes are placed. Okay. And then what happens is this tube seat can be, it's very important to know about the tube seat. These are circular and then thick. Also, it is sometimes called as the tube plate. Okay. So, circular thick metal sheet. Okay. So, they are used to hold the tubes at both the ends. Okay. Now, these tube seats can be fixed, may not be fixed. So, when fixed with cell called fixed head, cell and tube heat exchanger, and it may be floating, then we call it to be floating head. So, when both these tube seats are fixed. When both the tube seats are fixed at the two ends with a cell, then we call to be a fixed state cell and tube heat exchanger, and when one is fixed and the other is floating and the other is floating, then we call floating head cell and tube heat exchanger. Okay. Now, the idea behind this is that tube seat also will have pitch or square pitch. Tube should have the layout, and accordingly the tubes will be inserted into that. Okay. And then the next part is that floating head is used, one side is made floating. The reason behind this is that when there is a thermal shock, that means when there is the thermal shock or big difference in cell and tube side fluid temperature can be adjusted by the floating head arrangement. Okay. If you see again the figure, we will see that yes, here we can see that the projected part, it is here, in this case it is remaining as a floating head, and you can see that this portion is not fixed. The other side is fixed, one side is fixed, and the other side either it can be fixed head or it can be a floating head considerations. When it is a floating head, that means it can move laterally. So, there is a lateral movement is possible of this head. So, there is no when there will be a temperature difference, that can be adjusted by this head. Therefore, it is called floating head. This side is remaining as a floating conditions. Okay. So, this is now this is something about that different parts of the heat exchangers. There are many other things that has to be discussed. Now, I'll put a simple problem. Say what would be the equivalent diameter for square pitch and triangular pitch arrangements. Okay. So, this is now, if we try to see, as already we have discussed, this is the square pitch, sorry, and this is the triangular pitch. Okay. So, in this case, as I told that this is the PT and here it is the PT, center to center distance, and we know that in case of square pitch, what is the equivalent diameter D equivalent? If we say it is equal to 4 times the hydraulic radius, and that is equal to 4 into flow area. Hydraulic radius is defined as flow area by weighted perimeter. Okay. So, in case of wire tube arrangements, so for square pitch, so DE equivalent will be equal to 4 times flow area is, we know that flow area would be equal to PT square minus pi d square by 4 into 4, sorry. So, we can understand that this is the if PT square is there, then is the this is the area of the channel. through which it can flow, but it is being covered up by these portions are being covered up. So, these portions are nothing but 4 into this is one quadrant, because this is 90 degree, this is 90 degree, this is one quadrant of the total area of the tube. So, that means 4 multiplied gives you 4 quadrant, that means it is the area of the tube. So, cross sectional area of the tube is important. So, this cross sectional area will be that if DO is the outer diameter of tube, then it will be pi DO square by 4. Okay. And then what will be the weighted perimeter in this case? Weighted perimeter is again the first quadrant is pi d naught by total tube perimeter is pi d naught, okay, pi d naught 2 pi r into L per unit length if we consider. So, this is becoming now 4 into such. So, it is becoming now pi into d naught, that becomes the flow area by weighted perimeter. So, in case of square pitch arrangement, and in case of triangular pitch, so DE equivalent will be equal to 4 times. Now, we see that flow area is a equilateral triangle. So, the height of the equilateral triangle is given by root 3 by 2 into PT, that will be the height, this is h, and so area of the triangle will be half into PT into root 3 by 2 PT, that is the area of the triangle, okay, minus this is 60 degree. So, this is angles are 60 degree, okay, these angles are 60 degree. So, what will have 3 into 60 degree 180 degree, that means half of the area covered by the tube, fine. So, this will become now 4 into half into root 3 by 2 into PT square, half, that means root 3 by 4 into PT square, that is the area of the triangle, equilateral triangle, minus the area, half of the area of the tube, that is pi d naught square by 8. Pi d square by 4 is the area of the tube, divide 2. This is the flow area and divided by weighted perimeter. Again, in the similar fashion, weighted perimeter will be the half of the perimeter. So, it will be pi d naught by 2. Okay. So, this becomes the equivalent diameter in case of triangular pitch arrangement. So, I will stop here. Again, in the next lecture we will continue with the same thing. We will see that how different parts of the cell and tube heat exchangers and various other type of heat exchangers we will discuss in another 1 or 2 lectures, and then after that we will see how to design the heat exchangers. We will see some problems and we will see some methodologies, some how to and calculations procedures. Thank you.